Right, today we're going to study power series. The most general form of power series is going to be in the following form. It involves a variable. Okay, this is so-called power series and start from can be from 0, can be from that's an, and here x to the n plus x minus a to the n's power. Okay, if you write down all the details, that's the first term, second term, third term, and so on. Okay, and we want to study that convergence and try to determine the variables of try to determine the values of x for which this power series is convergent. Okay, and then definitely it's not always convergent, right? Sometimes it be divergent for some variable x. So let's take a look at the first example. Okay, this is a special example. This one, it's a very special. Okay, and a here is 0, and the coefficient is always a 1. Right, this can be written as 1 times x minus 0 to the nth power, right? So it's a special form. Okay. And we want to know when it's convergent, when it's divergent. Okay, so we take the partial sum, right? Okay, this is a partial sum, and we record the formula. Okay, this is going to be 1 minus x to the k plus 1 of x, and it's we know that this is a convergent to 1 over 1 minus x. Okay, if absolute x is less than 1. Okay, and as k approaches infinity. Okay, otherwise it is divergent. Okay, it does not have a limit. Okay, and it does not the limit does not exist. Okay, more precisely, is 1 minus x if absolute x is less than 1, and it does not exist or infinity if you want to say if the absolute x is greater than or equal to 1. Okay. Yeah, there is only one case when x equals 1, that's going to be infinity. Otherwise, the limit doesn't exist. All right, so this series, we can simply write, so we can simply write this function 1 of x as a power series. Okay, this is in other words, right? So when x absolute x less than 1, this function can be written as a series. Okay. Okay. Yeah. So in other words, this function f of x, okay, can be expressed as a power series for x absolute x less than 1. Now you may ask, how about x is not equal to 1? How about x is outside this interval? Okay, from negative to positive. Can we still express it as power series? The answer is yes. Okay, so this is a we know that. Okay, we know that f of x 1 minus x is defined is defined for x not equal to 1. Okay. So let's take a look at the graph. Okay, here's the 1. Okay. When x is greater than 1, when x is greater than 1, this is going to be negative. So the graph looks like that. When x is less than 1, x could be, right? I think this is a graph, right? Right, so this is 1. Now, can I express this function as a power series at any point which is not equal to 1? My answer is yes. So for any x not equal to 1, okay, I want to express it in the form in that form. Okay, cannot be just x, so it must be x minus z to the nth power. Okay, my question here. This is my question. And I think we can do that maybe around that interval, right? Now x cannot be arbitrary. Okay, otherwise, yeah, x cannot be arbitrary. So I think we're going to find the interval around a, which is still away from the 1, and I can express it as a power series. Okay, so that's how to do it. That's a technique. That's a this is a standard technique we're going to use it over and over again. Okay, so for x close to 8, okay, and so as long as the difference is less than equal to a minus 1. How about like that? Or 1 minus a. Okay, so 1 minus a is this gap. Okay, that's the radius. Okay. Right, so I'm going to do the following. I'm trying to show you how can I modify this expression and express as a power series. So this is doesn't matter, it's 1 minus a, okay? Let's put this one. All right, so here's f of x, okay? Because if this satisfies this condition, this implies x never be 1, okay? X never be 1, because this implies x never be 1. Okay, so this is always defined, right? All right, I'm going to express as I can let u to be x minus a. How about like that? Make it easy, right? So x is going to be u plus a. Okay, great. So 1 minus u plus a. Okay. So I get 1 minus a minus u. Then I take 1 minus a out. So I get 1 minus u, 1 minus a. Okay. Right? Okay, so this is something here, right? Now, what I see is u over 1 minus a is absolute value. That is going to be 1 minus x, right? And we already assumed that this is less than 1. So great. So I can have this series. Okay. So now I expand it. I take this constant out, 1 minus a to the nth power, and the x u, right? U is a x minus a. Okay, I can also move this constant inside. Okay, so we get a power series. This is true for x minus a less than 1 minus. Okay, this is Yeah, this holds for x over that interval. Okay, let me mark it over that interval. Okay. All right. Yeah, this is a good example. So a can be any number. Okay. For example, if a is 2, okay, if a is 2, then f of x 1 minus x is going to be 2, right? So 1 minus 2 to the n plus 1, and x minus 2 to the nth power. So 1 minus 2 is negative 1, so it also can be written as, okay, and this holds when x minus 2 less than 1 minus 2 is less than 1. Okay. So 1 over 1 minus x is always equal to that. And for x minus a absolutely less than 1. So if you look at the picture, this is the y-axis, this is x-axis, this is 1, right? I forgot, this is a graph. Yeah, that's a graph. Okay. So here's 2. So x minus 2 less than 1 is this interval. So over that interval, that piece of function, okay, that piece of function can be written as power series. Okay. It's going to be equal to this power series. In other words, for x in this interval, this power series is convergent. Not only convergent to that function, 1 over 1 minus x. Right, it's great. This is our favorite example. Okay, so next time if I ask you to express this function as power series around another point, and you know how to do it. But now there is an important theorem for a general power series. Okay, we consider power series. Okay, here's the thing. If we consider power series, okay, this is I use Cn here, okay, constant. Okay. For the power series, there is a number. Okay, this R could be 0 or finite or infinite. Such that, okay, that's 3 cases, right? Such that 1, this series is convergent. Okay, actually it's absolutely convergent, okay? Yeah, you don't have for x minus a less than r. 2, it is divergent. For absolute x minus a is greater than r. And we don't know what happens. We don't know, right? When absolute x minus a is equal to r, okay? We don't know, okay? So r is called the radius of convergence. Okay. Now, what that tells you, okay, this is an A, right? You're looking for X for which the series is convergent. And then the set of such X make the series convergent must be an interval around the point A. So this is R, A minus R is A plus R. Okay, it must be in that form. That is great. That is amazing. Okay, so it, you know, at the very beginning we don't know. Maybe it looks like that. Okay, this side is short, other side is longer. For the conversion, and that's not true. Okay. Okay. So, but we maybe, you know, the end point. We don't know whether it's convergent or divergent. Okay. So the right. So must be. Yeah. I didn't say anything about. So here's my remark. Okay. Okay. This is could be divergent, could be divergent. It cannot be determined. Okay. It's possible. It's case by case. Okay. So this we don't know, right? So when yeah, could be sometimes divergent, sometimes convergent. Okay. Okay. So okay. So when x minus a is going to be okay, we don't know. So it can be determined by other methods. Okay. So every power series there's a radius convergence. Okay. So let's go back to the example again. Okay. So this example, 1 minus a to the nth power, right? Okay. This is a is an arbitrary number. A is not going to be 1. Okay. We know this series. Okay. So we already showed that this series should be, it can be only convergent when absolute A, yeah, it is convergent. I can see that it is convergent if absolute, yeah, if this is less than R. What is R? R is absolute 1 minus A, okay? And divergent if this is greater than R, right? I is absolute, right? And how about when it's equal to R? When it's equal to, I think it's also divergent, but we can take a look. Okay, so so we get the radius, convergence radius. Now why it's convergent? Okay, suppose we don't know the relationship between this one and the previous function. Okay, so how can I check it? Right, this is the an terms, right? So let's take a look at n plus 1, absolute value of n. Okay. All right, so I'm going to get 1 minus absolute a is n plus 1. Okay, that is an plus 1, right? So then this will be n plus 2. Okay. Divided by this, then I have to turn this upside down. All right, so now we simplify it. What I got here is 1 minus a. Here's absolute x minus a. Okay. So we know that this power series is viewed as series, right? So we know that the limit, excuse me. Yeah. Okay, so the limit is going to be absolute A minus, right? Okay. So by the ratio test, when if this is less than 1, then this series is absolutely convergent. Okay, and if this is greater than 1, then this series is divergent. So from here, it's clear that, x, right? If and only if this is less than, right? So this is my R. So R equals 1 minus absolute is the radius of convergence. Okay. And so if you give me this series without telling me where it's from, I can tell this series is convergent over that interval. Okay, so this is the interval. This is A. This is my R, right? Okay, I is going to be absolute value for 1 minus A. And then it's easy to check this interval. One of the endpoint of this interval is 1. Okay. Okay. So you can see that one of the end point of R minus A minus R and A plus R is going to be 1. Okay. Why did not say A minus I is 1? Because A could be on the left hand side of it. 1. It depends. Okay. But this argument does not tell me what is so this argument only tells me the function, this power series is convergent for x on this interval, right? Yeah, how about when yeah, let's take a look at the special case. If absolute xa, right, is going to be this. Okay, so that means x minus a is going to be plus minus this. Okay, or x minus a over 1 minus a is going to be plus minus 1. Okay, so let's go back to this series. Okay, so I'm going to, I think I'm going to take one of these out. Right, so you will see that it's plus minus 1. So clearly it's divergent. Doesn't matter whether it's positive one or negative one. This is divergent. So for this particular power series, it is convergent only on this open interval. Okay. So I can conclude that is convergent if and only if, okay, x is between a plus capital and a minus capital, okay, where capital is 1 minus a, okay. It is divergent at the end point. So it defines a function, but we don't know what is that function generally. It defines a function, right? Because it's convergent. So it's convergent to something. And that function, yeah, sometimes it is an elementary function, sometimes not. But for this particular problem, it is we know that it's convergent to 1 of x. Okay. Yeah, as we already see that, as shown at the beginning. Okay. The series is actually convergent to, okay, convergent to 1 minus x. It's actually independent of a, okay, for x minus a less than r. Okay. Interesting, right? So there's a parameter a there in the power series, but the limit is independent of a. Okay, as long as a is not going to be 1. Okay. So sometimes this power series convergent to a function, elementary function, which you can express it. Sometimes we don't know. Okay, so you define a function, but that function cannot be expressed as an element function. Okay, but remember, power series is a generalized polynomial. Polynomial, you can talk about degree. Roughly speaking, power series is a polynomial of degree n equal to infinity. Okay. So consider the following example. Okay, negative n, here's x to the n. And this is a third root of n. Okay. I'm going to, so this is a power series around 0. So I know at the very beginning, I know that this series is a convergent if x is greater than a. It's divergent if absolute x is greater than r. We want to find out what is that special number r. Okay. Okay. So so let's determine it. Power series, most of cases, okay, this is the every term now n to the nth power. So this is a power function. So we usually use as a ratio test. Okay, unless we see n factorial there. So let's see. So this is my mark it. This is my n plus 1 over n. Don't forget the absolute value here, okay? Otherwise, you don't understand the ratio test. Okay, it's not like oops, I forgot it. No, this is it's a serious mistake if you don't put absolute value there. Okay, because this nth term might be negative. Okay, in my original statement, when you're trying to find a limit using ratio test, it's always absolute value there. Okay, I hope you put a note there. If you don't write like this, you will make mistakes, okay, in the argument. All right. So let's simplify it. So forget the negative sign, right? So this is an n plus 1 term. So this must be x, absolute x. Okay, that's the numerator. The denominator, if I wrote this, would be turned upside down. Okay. Then what do you get? Oh, this is a cube, right? You will get the third root of n. Sorry, the third root of n. Third root of n plus 1. And this is absolute x. Now, what is the limit of this? Well, you can also write this n over n plus 1. So the limit is clearly is going to be 1 times absolute x. Okay. All right. So by the ratio test, I know that this series, okay, right, is convergent if absolute x is less than 1. Divergent if this is greater than 1. So clearly I equals 1 is the radius of convergence. Okay. Now, do I need to know what happens when absolute x is equal to 1? I'm not asking you to to determine all the possible values for which is convergent. Then you stop here. Okay. We find the radius convergence. But if absolute of x, okay, is going to be 1. So if it's positive 1, okay, and I can tell that this series is convergent. Okay, this is a convergent. You know why? This is by the alternating series test. Okay, because this term Bn is okay decreasing to 0. That's it. Okay, it's obvious. Okay, now if x equals -1, then this series becomes, I think, negative 1 to that. So the -1 is gone. This is divergent. Okay, this is divergent. Oops. Right. Why it's divergent? By the p-series test. So now you can even get better, better information. Okay. So I can tell that my conclusion okay. This is a convergent if and only if x, I think 1, that does not include -1. If and only if x is greater than -1 and less than equal to 1, could be 1. Okay. And that's it. Okay, now, so we get a function because it's convergent. So you get some limit. That limit depends on the value of x. Okay. We get a function on the interval from negative to positive, including 1. But I don't know the value. Okay. Can I express f of x as some elementary functions which we're familiar with? We don't know. But we know that this is a function of x. It is a polynomial of a degree infinity. Okay, in other words, right? That's great. So we right now using power series, we can describe our functions in much more freedom. The power series still better than, still is good. You can see all the terms, although there are infinite many terms there. Okay, so it's better. So when you try to solve a function which satisfies certain differential equations, you are not able to express the solution as elementary functions you are familiar with. Maybe you can express it as power series. That's great, then you still can understand, see the function because you can see all the terms. And you can understand this function better than just abstract formula. Okay. Right, so that's our motivation to study power series, because sometimes we know there's a solution to some differential equations, but we cannot express it as elementary function, and we can we can express it as a power series. Okay, so take a look at this one. Okay, here 0 factorial means 1. Okay, 1 factorial is 1. Okay, 2 factorial is 1 times 2. Okay. Now this time we have n factorial. So we do the same thing. So this is n a to the n, right? So I'm going to, most time we use a ratio test, okay? Most time we use a ratio test. Okay, that works very well. Okay, so let's simplify it. This is n plus 1 factorial and x to the n plus 1 absolute value. And then this in the denominator I turn upside down, and here's n factorial. Okay. So what I got? I got absolute x. Then here's n plus 1. Okay, after simple. Then I take the limit. I find out that no matter what the value x you choose, this limit is always equal to 0. So in other words, this limit is 0, which is always equal to less than 1. So that means this series is always convergent for any x. Is convergent for any value of x. Wow, so this is pretty nice. All right, so we get a function okay, on the whole line. So we get a function f of x, okay, on this interval, which is the whole line. Now, what is that function? I will not tell you at this moment, okay? Sometimes this can be expressed as an elementary function. Nothing new here. You don't get a new function, okay? Okay, let's take a look at the next problem. Okay. We're trying to find out, find the radius of a convergence. Yeah, for the previous example, the radius of convergence is infinity, okay? So you think about this problem, okay? I give you half a minute or 1 minute to think about it. See, find determine the value x for which this series is convergent. So find the radius, maybe just find the radius of convergence. Okay, yeah, let's do that. Okay, I hope we already have answer. All right, let's do the usual, right? So I see, now we have to decide which method to use, right? You use a ratio test or use a loaded test? I think in this case, use a loaded test is easier than the ratio test. Okay, so this is the answer root. Put absolute value here, remember. In the ratio loaded test, there is absolute value there. Okay. Then you will get this, right? Now we're going to find the limit. I find out this limit is infinity if absolute x is not going to be 0. It is always equal to 0 if absolute value is 0. Okay. So there's only two possibilities, 0 and infinity. Infinity is greater than 1. So then by the rotor test, this series is convergent if x is 0, divergent if x is not going to 0. Okay. So there's only two possibilities. So that means the radius of convergence is 0. Okay, that's the special case. Now, if you use a ratio test, it will be pretty challenging. If one uses ratio test, okay. If you use a ratio test, then you have to look at this limit, right? So then you have n plus 1 to the n plus 1 term, you see? And this part is okay. Then divide by n in the term, right? So the problem is how do you get a limit of this, right? You cannot just say, oh, this is infinity, right? You have to tell me why it's infinity. Okay, not everybody can do that, can prove this part, the limit is infinity. Okay, let's take a look at this. Okay, that depends on, how much math you learned before. Okay. So I want to simplify and find the limit. I find out that here's n plus 1. So I can make it, right? Separate them, then I can put them together. It's 1 plus 1 over n to the nth power, n plus 1. Then you realize that what is the limit? This limit is going to be e. That limit is going to be infinity. So the product, it approaches infinity as n. If you can write it like this, I can say, oh, great, good job. Okay? So the limit of this coefficient is infinity. But clearly, right, you have to do more work than the previous method. Okay. Right. How about this? Instead of n to n's power, I put n to the 2021 x to the n's power. Okay. Now what? Okay, I'll let you to try again. Okay, find the radius convergence. Okay, determine the value x for which this series convergent. Right. So I think I can either use a ratio test or use a row test. Doesn't matter in this case. Okay. If you use a ratio test, you still get the same result. Okay. So let's use a ratio test. No problem. Okay, maybe you use a row test. Let's use a row test. Sorry. All right. So so that is going to be n to the 2021. Okay, absolute x to the n and the 1 of n. Then you switch it, you get, right? Now, what is the limit of that coefficient? Well, this is going to be n to the 1 of n and then 2021. Doesn't matter how big of that number. This limit is always equal to 1 as n approaches infinity. Okay. So that means the limit is going to be absolute x. So you know what is a radius convergence, okay? So we know that by the rotor test, if you use a ratio test and say by the ratio test, okay, I can see that this series, okay, this series is start from 1, right? And to the 2021 x to the n is convergent if x is absolute x is less than 1. Divergent if the absolute x is greater than 1. So that means the radius of convergence is 1. That's it. You don't need to worry about what happens when absolute x is equal to 1. I'm not asking you to determine all the values of x, which the series is convergent. Now, there is a so-called interval of convergence. Then you have to look at the endpoints, okay? So it depends on the problem. Okay, so take a look at the next problem. This is a 2 to the n and natural log of n, and here x minus 1 to the power n. And we want to determine the value of x for which, yeah, let's say find the interval, yeah, find the interval of convergence. So that means I have to determine the end to check the endpoints too. Okay. So let's use a ratio test. I don't think we should use a root test because the nth root of natural log n, I don't know. I have no clue, right? So use a ratio test. Okay. So I'll get, oops. 2 to the n plus 1. Here's the absolute of x minus 1 to the n plus 1. Natural log of n plus 1. And turn this upside down to the n. N. Right? And the natural log of n. Okay. So I get 2. Then I also get absolute x minus 1. Then there's addition term here which involve n. I think clearly that would be limited to be 1. And this part is limited to 1. Okay, why is the limit of this 1? Yeah, I can discuss this a bit later. Okay, so the limit is 1 as n approaches infinity. So that's my limit right now. So now clearly this series is convergent. N start from 2. If absolute x minus 1 is less than 1/2, right? And divergent if this is greater than 1/2. So clearly r equals 1/2 is the radius of convergence. Okay, but we want to know what is the interval of convergence. That means we want to know what happens at the end point. Right. At the end point, the two cases here. So x minus 1 equals 1/2. Right. If x minus 1 equals 1/2, then this series is going to be I think it's just equal to natural log of n. 1 of natural log of n. The reason is there's, right, 2 to the n, x minus 1 to the n, right? So this is supposed to be 1. 1 to the power n, so it's 1. Okay. Now, why this is divergent? Why this is divergent? Okay, let's prove why this is why must be infinity. And how do you prove it? You cannot say obvious. In this particular case, it's not obvious. But I know I know about P-series test, right? I know 1 over n is convergent. But natural log of n goes smaller than n, okay? So we have to use this property, okay? Natural n is less than or equal to n. And then you ask me, how do I know that? Well, we have to prove it, okay? Let's accept this. Yeah, let's accept this. Then, right? And then this is infinity, right? This is because then it makes the one on the left hand side is the infinity. Okay. But the question is, how do I know natural log n is less than equal to n? Well, I have to look at the function. Natural log x minus x. I know f of 2 is natural 2 minus 2. This is less than 0. Then you say, how do I know that? Well, less than natural log e, right? Because 2 is less than e, I know that. And e is going to be 1, natural, it's minus 2, it's less than 0, okay? Then the derivative is going to be 1 over x minus 1, which is also less than 0, because x is greater than 2. Actually, x is greater than 1 is enough. So that means the function is decreasing. So that's if x is greater than or equal to 2. But that's also less than 0, right? So that means natural x minus x is less than 0. Okay. That implies natural x is less than x if x is greater than 2. Okay. See, this is a proof using calculus. All right, so it's not easy, right, to give this argument. Okay, anyway, it's divergent now. Okay. Use a limited comparison test. Okay, another way to do is to prove it's divergent is you have to choose. So your n is a natural log of n, right? So you can choose a bn, just say n. Then you compare it. Compared to with this, okay? So that means you get n over natural n, that should be infinity, okay? Once you prove that's infinity, that means this is going to be greater than or equal to 1 for large n, let's say greater than or equal to capital. We don't need to know exact value. Then n is greater than or equal to bn. Bn is 1 over n. You know, n is going to be natural log n. You still can get this conclusion, okay? And using that, you can prove that the series is divergent. Okay. All right, so now let's look at the case x minus 1 equals equals -1/2. Okay. If it's equal to -1/2, then this series is going to be all right, and clearly it's convergent, okay? Is convergent. The reason it's convergent just because by the P-series, by the alternating series test. Yeah, the sequence, you can say since Bn This is decreasing to 0. It's obvious. All right. So now you get the following conclusion. This series is convergent on the interval including the negative point. So 1 minus 1/2. Okay, and the 1 plus 1/2 at that point does not include. So I is that. This is the interval of convergence. Right. Outside this interval is divergent. All right, so let's take a look at the next one. This is from the book. Yeah, let's take a look at this. Yeah, well, it can simplify. Yeah, that's fine. All right, so take a look at this. This will be my last example to discuss here. All right. So you just view the like a series, okay? And the question is when it's converging, when it's direct. You have to find the limit, okay? Using the ratio test, okay? Or the rotor test. I think I should use the ratio test. Okay. This is my n. Okay, and you simplify it. So this will be n plus 1, natural log of n plus 1 square, x absolute 2n plus 1. And then the denominator, 2n, n, natural log of n squared. Okay, so let's simplify it. I cannot get rid of them, right? So I put an n plus 1. Similar terms together, natural log of n, natural log n plus 1 square. Oh, this side is just square. Okay, then this part approaches 1, and we already did that. Natural n over natural log of n plus 1 approaches 1, right? So the limit is just x squared. So the limit is x squared, then clearly by the ratio test. So for, as you see that for the power series, right? More likely again to use the ratio test or root test. But then at the end point, sometimes we use a alternating series test, okay, to check whether it's convergent. Okay, so by the ratio test, this series, okay, it starts from 2, right? Is convergent if absolute x is less than 1. Divergent if absolute x squared is greater than 1. So clearly, absolute x squared less than 1 is the same as absolute x is less than 1. So the radius r equals 1 is the radius convergence. And that means for x, if the absolute x is less than 1, and that is convergent. Okay, this is the largest possible value we can get. All right, so we have to look at the end points. Right, we have to look at the end points. So what happens if absolute x is equal to 1? Right? If we ask you to find the radius convergence, you're done here. But if you want to find the interval of convergence, you needed to look at the end points. Right? So let's continue. So if the absolute of x, if absolute of x is going to be positive, okay, I think it doesn't matter, positive or negative, okay, plus minus 1, because we already have the square there. Yeah, at the very beginning, I was trying to discuss this in two cases. Now I just realized that when it's squared, it's just always equal 1. So the numerator is always equal 1. So you end up with this series. Is it convergent? Do you still remember that? All right. So for this one, let's call the Bn. Yeah. So Bn equals 1 over n natural log n squared. Okay. So that is going to be f of n. So my f of x equals x natural log x squared. It's going to be decreasing function, positive, right? On the interval from 2 to infinity. So here I'm going to use the integral test. Okay. So I use a substitution. I let u to be natural x, then du equals 1 over x dx. So this is going to be, yeah, it's natural log 2 to infinity, and nothing, I just use square du, okay? So clearly it's a finite. Yeah, that's going to be u negative. Okay, this is the antiderivative, and my answer will be natural log 2 to the negative 1. Okay, so yeah, let's give a few steps here. This is a finite. You can evaluate. All right, so that implies this series is a finite. Okay, not only finite, even you can estimate. Okay, so that means this series is always convergent at the end point. Then the interval of convergence is going to be from -1 to +1. Okay, absolute value greater than equal, less than equal to 1. Okay, that includes all the points. Okay. That's it. The power series is just a special series. Right? But you have to use all the methods we learned to determine the interval of convergence. If you just want to determine the radius convergence, probably just use a ratio test and the root test.